Let's now learn how to work the third type of chemical composition problem, going from empirical formula to molecular formula. But first, let's review what we've done so far. We started out learning how to convert a molecular formula to a weight percent. Then the next thing we learned how to do was take a weight percent composition and convert that to an empirical formula. And now what we're going to learn how to do is to take and convert an empirical formula into a molecular formula. And those are your three basic types of chemical composition problems. Recall that the relationship between molecular formula and empirical formula is that the molecular formula is equal to the empirical formula times the number of empirical formula units. The chain link is equal to the individual chain link times the number of chain links. Now we do have a problem when we look at this equation, and it's this. Although we have calculated the empirical formula, what we have not calculated is the number of empirical formula units. And similarly, we're looking for this, so we do not know it. So the problem is we now have one equation and two unknowns, and that is not solvable. So the key to working this is to find an equation that does not have two unknowns. And we're going to do that with this bottom line because we know that the molecular weight or molar mass is going to be equal to the empirical weight times the number of empirical weight units. Back to our chain analogy, the weight of the chain is going to be equal to the weight of one chain link times the number of chain links. And here's what that means at this point. We now know this. We can calculate it because we now have the empirical formula. One way you can tell you have this type of problem where we're going from empirical formula to molecular formula is that the molar mass is going to be given for your product. And this is not an unreasonable to assume you're going to have that. Just as calculating the percent composition of unknown materials is pretty easy in an analytical lab, so too is determining the molecular weight for formulas. It's quite common that we know what the weight of a compound is, and we don't know what the compound itself is. But what we don't know is the number of units. But this equation here, molecular weight equal N times empirical weight, allows us to calculate that. Why? Because we now have one equation and one unknown. So we can now calculate N. And if we can calculate N, then we know it for this equation as well because N does not change. It's the same formula. And now notice what we have. Now this top equation, we now only have one unknown, and we can now solve for that, and we will arrive at where we need to be. So, we know the empirical formula is HO, so we can calculate the empirical weight. That's the weight of one hydrogen, which has an atomic weight of 1 gram per mole, and one oxygen, which has an atomic weight of 16 grams per mole. Adding those together gives us 17 grams per mole for HO. We were given that the molar mass is equal to 34. So in that case, we have a simple math equation. 34 is equal to N times 17. So therefore, N is equal to 34 divided by 17. So therefore, N is equal to 2. This number is now 2. So we know that this number is 2. Now it's a simple matter of solving this equation. N is 2. My empirical formula is HO. So what's my molecular formula? My molecular formula is 2 of these. Now, that's not the real formula. We have to deconstruct this. So let's finish this off. So what do we have? We've got 2 of these. So how many H's do I have? I have 2 H's and I have 2 O's. Therefore, my formula is H2O2, and that is correct. You can now work any of these types of problems. You can now convert molecular formulas into weight percents. You can convert weight percents into empirical formulas, and you can convert empirical formulas to molecular formulas using this technique.